So let's look at some examples of how paleoclimate tells us the past climate records and the various processes that are recorded. And this is helpful because we need to know with climate change the serious perturbations we are making to the climate system, where we may be headed, or what are the possible modes of variability in the climate system. We don't necessarily know all that, but paleoclimate is like a rear view mirror which tells us what's come before. Of course, different analogy. The rear view mirror tells what's coming behind you, but you can think of that as we keep rushing forward with increasing CO2, what is possible from the past, right? So we're looking here at delta O18. So less global ice volume and warmer climate means the O18 depletion is less, and greater global ice volume and colder climate means that the foraminifera will have more depleted delta O18 present when they are calcifying, because more of the delta O16 has been locked into glaciers. So record of oxygen isotope fractionation from seafloor sediment cores reflecting general variations in global climate, including global ice volume over the past 5.3 million years. This is kind of the critical time scale for evolution of humans themselves, because the old world monkeys, new world monkeys, and our evolution of bipedalism from our closest ancestors like chimpanzees and gorillas all happened somewhere around here, and then the various hominid species evolved around here, and we have had a regular beat of 100,000 year cold and warm climates, glacial, interglacial climates, or ice ages, and melting of ice ages has happened here. Okay, so all these things, very rich record has been locked in. So you can see the Pleistocene starting from about 2.5 million years. I mean Pliocene going back before that, and Pleistocene starting around 2.5 million years ago. Note the reversed y-axis. So typically in paleoclimate we go from the past time to the present time, which makes sense. It is still going forward in time, but you're starting way back when. That's all. So lesser values of delta O18, which means higher, so the scale is reversed. Higher delta O18 is here, lower is up here, just to give it a sense of temperature going from cold to warm. So that works very well. Lesser values of delta O18 higher on the graph represent warmer global climate and lesser ice volume. The record is a composite of 57 globally distributed records produced by Lisiecki and Maureen Ramo. The inset zoom is into the last 150,000 years, so approximately the last ice age to the present Glacial Age, revealing the most recent glacial cycle. The boundary between the Pleistocene and Holocene represents the epochs at 11,700 years ago. So you can see that there are different time scales here. We talked about the obliquity time scale of 41,000 years, precession time scale of 23,000 years, eccentricity cycle of 100,000 years, but the internal feedbacks in the system, ice albedo feedbacks, so-called ice albedo feedbacks, which means if the ice cover is large, more of the sunlight is reflected, so favors further cooling. If glaciers begin to melt because of orbital changes, then albedo decreases, more energy is kept, so a glacier can retreat very quickly in this warming phase because more and more energy is kept into the system, more and more glacier is melted, albedo is reduced further and further, and so on. So due to these kind of internal feedbacks, you can get multiple time scales. What determines the time scale at any given period of the paleoclimate is not always very well understood. For example, why we went from this relatively higher frequency to kind of the obliquity time scale of 41,000 year time scale here to the eccentricity time scale of 100,000 time scale here are not fully understood. Lots of hypotheses exist, a lot of explanations are given, but if you look at the end of the beginning of the last ice age around 150,000 years ago, so you are going from warmer higher, so greater global ice volume and colder climate to deglaciation, and then the slow cooling over these periods to about 21,000 years ago when the ice age peaked, and then we abruptly came out of it to come into the Holocene when modern human being as agriculturalists emerged. So end of the Pleistocene and beginning of the Holocene, somewhere around 11,700 years ago. So you can clearly see here that the deglaciation can be very rapid in time. So the warming phase, which is what we are in now with global warming, can be very abrupt. As glaciers begin to build, albedo increases, more energy is lost back to space that is coming from the sun. As atmosphere cools with the cooling, its capacity to hold water decreases, so the snowfall rates begin to decrease, so the glacier grows slower and slower. So building the ice glaciers takes a long time, whereas melting the glacier can be very abrupt. And we have to worry about this because right now we are melting glaciers. Okay, so here is the record of oxygen isotope fractionation from the North Greenland Ice Core project, or GRIP project, reflecting general variations in northern hemisphere climate, including the response to global ice volume over the last 123,000 years. Only the last 50,000 years are shown here. So it's part of this part of the record here. Okay, greater values of delta O18 higher on the graph, so we have flipped it here now, represent warmer northern hemisphere climate and lesser global ice volume. So we are looking here at oxygen isotope from the ice core itself, and lesser values of delta O18 lower on the graph represent colder northern hemisphere climate and greater global ice volume. Note that greater details in the ice core record than in the equivalent time period of seafloor sediment cores, rightmost here, so the time resolution here is much lower than here because of the way the proxies are produced. Sediment is produced by biological activity, leaving the signature, which is very, very slow compared to the glacier, leaving bands of air bubbles and so on within the glacier. So those differences have to be dealt with. Okay. Danskard-Ushker events, the last glacial maximum. So these events here of pulses of warmer and colder climates are called Danskard-Ushker events after the people who discovered them, and the last glacial maximum happened here around 21,000 years or so ago, where the coldest temperatures of the recent ice age was reached, largest ice volume, glacier volume, and then we started to come out of it. Glaciers started to melt, so we started to head towards warmer climate. There was a hiccup and a sudden cooling because of, again, the thermohaline circulation. So as the glaciers were melting coming out of the last glacial maximum, the glaciers were melting in bits and pieces. They had gouged out the superior lakes in the North American continent. For example, Lake Agassiz, one of the Great Lakes, one of the lakes was dammed by a glacier that was not melted. That glacier broke and suddenly released a lot of the melt water that was behind it, and that came onto Labrador Sea. And what did it do? If you put a lot of fresh water on a region where deep water is forming in the North Atlantic, then even the evaporation and cold temperatures make it harder for the density to get large enough to sink. Because you have put a lot of fresh water on top. So suddenly there was a recooling because the thermohaline circulation, which brings heat and salt to the North Atlantic, was suddenly weakened because of this weakening of the Atlantic Meridional Overturning circulation. So that is recorded very clearly here, called the Younger Dryas, and the great thing about it is it gives you a sense of how quickly the system can oscillate back and forth. So this is kind of the idea in the movie called The Day After Tomorrow, where scientists are reporting very warm ocean temperatures off of Greenland, and suddenly there is freezing of New York City with the hero and his girlfriend stuck in New York Library, which is frozen over. So the idea there is that the warm ocean temperatures melted the glaciers over Greenland, which is happening right now, and released a lot of fresh water and reduced the deep water formation, which means North Atlantic heat. The Gulf Stream and the North Atlantic current don't bring as much heat anymore, so it begins to freeze again. So you go from very warm ocean ending up melting the glaciers, putting a freshwater cap, changing the Atlantic Meridional Overturning circulation, and refreezing the planet. Okay, so that's kind of what happened here, and we came out of it, and then we have been basically at a very mild temperature in terms of the deviations from the mean over these last 10 to 12,000 years, where we have evolved the way we are now with all the energy consumption, innovation, but very heavy energy lifestyle, which is increasing the greenhouse gases and kicking the climate very, very hard. So this is the time series of the observed strength of the Atlantic Meridional Overturning circulation, AMOC, the part of the thermohaline circulation in the Atlantic Ocean, from transport measurements taken by rapid array. So this is a very short time series now, from 2004 through February 2017. The thin line shows the 30-day smoothed data. So overturning is estimated using other ways. There is no direct way to measure it. Okay, so you can put a chain across the North Atlantic from North America to Europe and estimate how much water is passing north and south. The thin line shows the 30-day smooth data. Original data set is 12-hourly resolution. And the thick line shows averages before and after March 2008. So overturning here reduced by 2.7 Sverdrups. A Sverdrup is a million meter cube per second. So that's a 14% decrease since 2008. So in the next chapter we will see the consequences of this in terms of the warming pattern in the North Atlantic. Okay, so there is some indication that the thermohaline circulation is responding to global warming in terms of changes in the deep water formation rates, changes in the amount of heat being transported, but there are lots of debates about exactly how this is happening. So I will leave that for the next podcast, and we won't actually get into a lot of the details there, but you can read. There are lots of many interesting articles on that, whether it's a human impact or whether it's natural variability. This is always a critical aspect to resolve. When you detect a change, you detected the change, but then there is something called attribution, where you have to say whether that change that you detected is because of natural changes, like changes in solar radiation or changes within the Earth system itself, or whether they are attributable to human impact on the climate. That's always tricky, so we'll see some of that later on. But for now, let's leave this here and then complete the thermohaline circulation and paleoclimate in the next podcast. Okay.